In this video, I'm going to talk about the product rule for exponents. Now, the definition of this rule is going to be x to the power of a times x to the power of b equals x to the power of a plus b. So as long as we have like bases, as long as these bases are the same things and we're multiplying, we can just add up these exponents. So I'll show you how this works using this first example. We have 2 cubed times 2 to the 4th. So based on our definition here, it should be 2 to the power of 3 plus 4, which is going to be 2 to the power of 7. And if you work that out, you'll see that's going to be 128. I'm less concerned about the 128 and more concerned about this 7. So where did that come from and why does that work? So this 2 cubed, if we were to put this out in expanded form, we would see it's 2 times 2 times 2. Now this 2 to the 4th, if we were to put that in expanded form, that would be 2 times 2 times 2 times 2. So how many 2's do we have here? Really, it's a matter of counting. 1, 2, 3, 4, 5, 6, 7. So that is where our 2 to the 7th came from. Because again, remember, exponents just mean we're going to use this factor 3 times and this factor 4 times. So as long as the bases are the same, or we can say the factors are the same, then it's just a matter of adding up these exponents. Okay, so let's look at another example, how this will work out. If we have 3 times 3 to the power of 5, what's that going to be? Well, 3, since it doesn't have an exponent here written, it's understood to be a 1. So anytime you have a base and the exponent's not written, it's going to be a 1. So in expanded form, this would be 3, and then you would have 5 3's here. 3, 3, 3, 3, 3. So how many 3's do you have in all? Well, it's a matter of counting. 1, 2, 3, 4, 5, 6. So 6 3's. But we knew that was going to be the case because 1 plus 5 is 6. And again, I'm less concerned about the fact that this is 729 and more concerned about the fact that we have this 6 right there. Let's go ahead and take a look at some examples that use variables instead of actual numbers. In this first one, we have x squared times x to the 7th. Well, because our x's are the same for the bases and we're multiplying, we can go ahead and add those up and we can say 2 plus 7. And what is 2 plus 7? Well, 9. So x squared times x to the 7th will really be x to the power of 9. The next example is y times y cubed times y to the power of negative 2. So I notice that my y's are the same in all cases, so all my bases are y. This one doesn't have an exponent, so we need to put a 1 right there. So don't forget about him. Y to the 1 times y cubed times y to the power of negative 2. Well, when I add all those up, it'll be 1 plus 3 plus a negative 2. That's going to give me 1 plus 3 is 4, and 4 plus a negative 2 will be 2. So this answer right here is y squared. The next example we have is a times a cubed times another a. So once again, since there's no exponents written above these a's, we need to understand that they are 1's. So we're going to have a to the power of 1, 3, and 1. So 1 plus 3 plus 1. So really this will be a to the power of 5. Our next example is y squared times y to the negative 5th. Well, as we've seen already, when we add up these exponents, we're going to get 2 plus a negative 5 will be a negative 3. The problem with this is we have a negative exponent. So we have to go back to the previous section and say, well, how do we fix this if we have a negative exponent? We're going to write 1 over y to the positive 3. So remember to take the reciprocal of this to change this negative exponent to a positive 3. Our next example has x times y to the power of negative 2 times x cubed y cubed. Well, notice here we have multiple variables. They're not all the same variable. That means we have to group up the x's together since they have the same base, and then group the y's together since they have the same base. I'll go ahead and rewrite this with the groupings. So we have an x and an x cubed times a y to the negative 2 y cubed. So now that I have them grouped, I can see that my x's right here are going to be a 1 plus 3, so x to the 4th, and then my y's are going to be negative 2 plus 3 is y to the 1. But since this is a 1, I'm not going to write it because it's understood, or its default value is going to be a 1 if nothing is written. So I'm not going to go ahead and write that 1 there. I'm just going to leave it x to the 4th y. Okay, this next example has a squared b cubed times a to the negative 4th b. So like I did in the previous example, I'm going to regroup my terms. I have a squared times a to the negative 4th, b cubed, and then a b. So what will that end up being? Well, I have a squared and a to the negative 4, so I have 2 plus a negative 4 will be a to the negative 2, and then b cubed and b to the 1 power will be b to the 4th. But like we saw in a previous example, we can't leave this negative exponent there, so we have to take the reciprocal, and since it's in the numerator, we need to put this in the denominator and make it a positive exponent. So our final answer will be b to the 4th, which is positive and stays in the numerator, over a squared. In our next example, I have 3m to the power of 7 times 8m to the power of negative 2. So in here, my coefficients are 3 and 8, and it looks like I'm multiplying. So I'm going to multiply these values like I would any other value. 3 times 8 is going to be 24. Now I can deal with my variables like I've been dealing with my variables. M to the power of 7, m to the power of negative 2. So 7 plus a negative 2 makes 5. So this example is 24 m to the power of 5. My next example is pretty similar, where I have some coefficients out here. So negative 7 times 3 will be negative 21. And p right here is understood to be p to the 1st. So I'm going to put my variables together. So p to the 1st and p to the negative 11th. 1 plus a negative 11 actually makes p to the power of negative 10. But I don't like to have this negative exponent here, so I'm going to fix it. But be very careful, because these negative values out here, this negative 21 and this negative 10, they have nothing to do with one another. So you've got to make sure that you keep them separated. So we have negative 21 in the numerator, which he's going to stay there because there's no negative exponent telling him to move, over p to the power of 10, because once we take this negative 10 in the numerator, put it in the denominator, we have a positive 10. Two more examples to go. In the next to last example here, we have a fraction, and on the top we have x times x to the 4th. So we can automatically write that as x to the 5th, because we know this guy is going to be a 1, and 1 plus 4 is 5. Our denominator has y's, y to the negative 5th times y to the 1st times y to the 4th. So when we add up all those, negative 5 plus 1 is negative 4. Negative 4 plus 4 is 0, actually. And remember, as long as y doesn't equal 0, because 0 to the power of 0 is undefined, all other powers of 0 are just 1. So if we have x to the 5th over that 1 value, we can rewrite this as just x to the 5th, because we don't need this denominator if it's over 1. In our final example, we have y to the power of negative 1, y to the power of 0, y to the power of 1, and then y squared. So again, we're just going to add up all of our exponents. Negative 1 plus 0 is negative 1. Negative 1 plus 1 is 0. And then 0 plus 2 is going to be 2. So this one ends up being just y squared. So this is the product rule for exponents.